As promised, we're going to take a look at some more complicated inverse functions. So we're starting with a square function. Remember to write the inverse. You switch the x and the y. You can think of f of x as your y and solve for y. So we've got x equals y squared minus 9. To solve for y, we will add 9 to both sides. And then take the square root. Now remember, when you take the square root, think about a parabola. It does not pass the horizontal line test, which means its inverse is not a function. In order to get all of the function in the inverse, we have to do the plus or minus when we take the square root. So if you think about this graphically, sketching it real quickly, our original function was the x squared, the parent function, shifted down 9. So it might look a little something like this. So in order to get its entire inverse on the graph, think about reflecting it across that line, y equals x. We're going to get something like, let's see, x plus 9, so it would be shifted. Actually, I shifted it the wrong way, but something like that, where you would have the square root function above and below the graph to get the entire parabola. So to determine the domain of our function, or actually it's not a function, to determine the domain of our inverse, remember for a radical, whatever is under the radical needs to be greater than or equal to 0. So we set x plus 9 greater than or equal to 0, and then subtracting 9 from both sides. So our domain is any x value that's greater than or equal to negative 9. Inverse of a rational function. Again, we're going to switch the x and the y, so we have x equals 5 over y minus 3. First step, I know I'm not doing steps anymore, but when we did this last time, this was probably the most challenging one we saw. So when you have a rational function, I'm going to be writing these steps specifically for a rational function. Get y out of the denominator by multiplying. Now, what you multiply by is the entire denominator. I don't normally show my work like this, but again, I don't want to lose anyone. When we multiply by that entire denominator, the whole thing cancels. On the left-hand side, we're going to distribute our x. And then you get all y terms on one side of the equal sign. We already have that, but sometimes we have more than one term with a y, and we need to get them all together. Now, as you're getting all of your y terms on the same side of the equal sign, you want to get everything else on the other side of the equal sign. So I'm going to add 3x to both sides. This case, we don't have it, but if you have more than one y term, you will need to factor out the y. And then divide by whatever's not y. So in this case, to get y alone, I'm going to divide everything by x. And again, we can use that function notation, f inverse of x equals 5 plus 3x over x. All right, so there's the process of solving for the inverse. Now we need to look at its domain. The domain of the function is what would make the denominator defined. In this case, we talk about a restricted domain. So looking at the denominator of our inverse, x cannot equal 0. Now there's an additional restriction because it's the inverse of 5 over x minus 3. And because 3 makes our initial function undefined, we can't have that value in our inverse domain either. So when you're looking at the domain of an inverse function, because this is defined as the inverse of f of x, whatever makes the original function undefined would not be possible to substitute into the inverse either. All right, so now we're looking at one a little bit more complicated, but the same steps. So the first thing we do, think about that first step that I gave you. obviously switching the x and the y's. Sorry, that should be an x equals. And when you've got a rational function, you will have y in the denominator. So the first thing we want to do is multiply both sides by the denominator to get that canceled, leaving us with just y in the numerator. And when we distribute our x over here, we'll have no denominator, which is great. That's what we want. Next step, get all terms with a y on one side of the equal sign, everything else on the other side. So the easiest way to do that on this one is to subtract xy from both sides. If you have more than one term with a y, you have to factor the y out. So we're going to do that on the right-hand side. We're going to factor y out of our expression. Y divided by y is 1. The negative xy divided by y is negative x. And then to get y alone, we'll divide everything by that 1 minus x. Or again, using the function inverse notation, f inverse of x equals 7 over 1 minus x. For the domain, we need to look at what makes our inverse undefined. In this case, if x were 1, that would make the denominator 0, so x cannot equal 1. And we have to look back at our original function as well. We had x plus 7 in the denominator, so x cannot equal negative 7 either. Last example, determine if they are inverses. This is the one where we do the composition. We substitute one function into the other function to see if they simplify to just x. So taking the entire g function and substituting it into the f function for x, we get 5 over negative 5 over x minus 4 plus 4. To start our simplifying, we are going to get a common denominator in the denominator, which would be x minus 4. So I'm going to multiply my 4 by x minus 4 over x minus 4. Simplifying, my numerator is still at 5. In the denominator, I'm going to distribute the 4 here. So I've got 4x minus 16. I'm going to combine that with my negative 5. So I will have 4x minus 16 minus 5, or 4x minus 21. And then in order to finish simplifying, I need to multiply by the reciprocal. I've got a fraction divided by a fraction. So I'm going to take my numerator and flip my denominator. Now you might already be thinking, I'm not seeing this simplifying, and I'm not either. But our last step is to distribute that 5 into the numerator. So we have 5x minus 20 all over 4x minus 21. Neither one of those expressions factor, so nothing's going to simplify. So no, these are not inverses. And your U-try questions.